Thank you very much for coming. And brief introduction for our today's speakers. So Renato Renner, he's a professor at ETH Zurich, and he is working in quantum cryptography, quantum error correction, and recently he started to work also in gravity and black holes, so quite a lot of interesting stuff. And Nicolas Gisin, he is a professor here at Geneva University and also in Constructor University, and he's working on both sides, theoretical and experimental, of quantum science, and he implemented some important protocols of quantum information processing, and also worked in quantum networks, quantum non-locality, and much more. But today we are going to talk about quantum mechanics interpretations, and it wasn't planned like this, but it seems that our debates, they're actually in the middle of the series of such debates, and first one, it was 1 month ago in between Renato Renner and Fröhlich, and in 1 month it's going to be a debate in between all three speakers. And now I'm going to emphasize that actually it's a very hot topic and a lot of people are very emotional about it. And I'm going to talk about... Is it fine? Yes. Okay. So I'm not going to tell about opinions of our today's speakers, I leave it for them. But I want just to show that it's a very interesting topic. And I will start with a paper of Fröhlich, who said that it's an intellectual scandal that we still didn't manage to find a good interpretation of quantum mechanics. And Nicolas Gisin thinks that some of these interpretations, they can infect the society. Renato Renner is a bit more patient about this, and he thinks that we just need to make some Gedanken experiments and move to the technical path. And what we are going to do today, we actually really feel that we need to change the station and turn the debates into a technical question, but also we want to add some romantic in our today's debates, and we want to do this for those who love life. And that's what we are going to do today on our Quantum Club meeting. And before we start, I would really ask our speakers to define the following notions if they use them in their talks. Or if it's not possible, and I know that sometimes it's not possible to give precise definition, I would ask to give at least an intuition of what they mean, because otherwise we can continue with the debate later. And I'm talking about the following notions like measurement, agent, and measurement device. So from here, that's all from my side, and Renato, I guess now the floor is yours. And thank you for your attention.
Okay, so welcome. I'm very glad to see that so many people are interested in this debate, and I'm sure it's going to be interesting. As Anna just said, I'm already a bit, I got some practice with this. I had a very interesting conversation with Jörg Fröhlich, and we will have a showdown in a month from now in Lugano. That was the other debate that was mentioned, where all three of us that you saw in the picture will meet and debate. And I think the situation is that we all have rather different opinions on quantum mechanics, but at least now, after today, there will only be one opinion, I hope. Let's see. So, as I said, I had a debate and it had a similar format, and I will show some slides that I also used for the former debate, so I hope there is not too much overlap in the audience that you will find this boring, but of course I repurposed it and also had to adapt it a lot because of course I have to take up the particular opinions of my opponent now today and see how this goes. So this was actually, I wasn't aware of the fact that Jörg Fröhlich was complaining about the same, but I'm also starting with this fact that quantum mechanics is now 100 years old, and there has been a lot of reflection about it. People have thought about it for a very long time. And the outcome of that is that we arrived at extremely many different views which are not mutually compatible. So rather than converging, the 100 years have actually resulted in a very diverse view about what quantum mechanics should be and how it should be understood and so on. And now, if you look at this diagram and compare it to the situation we have in experiments, then this looks like this. So the experiments are not able to distinguish the different views on quantum mechanics that we have today. So there is not an experiment as of today that tells, for example, people now we are all convinced that many worlds has been ruled out. Maybe people are ruling it out for theoretical considerations, but there is no experiment we could do to falsify that. And the same is true for all the other interpretations as well. And so we still are in this situation where the opinions among the physicists is quite diverse. You see it on this slide. This was some survey that was made 10 years ago, but I think this hasn't changed a lot. Now, I think if you look at this diagram, it's really somehow a situation which looks a bit uncomfortable, but one could also say it's a very interesting situation. And I'm not only looking forward to the debate because it's going to be fun to discuss with Nicola. I think it's generally an extremely interesting topic to do research on, because obviously it's an open question. We have a situation where experiments couldn't decide, but now you could, of course, be worried and say, okay, maybe this is just a philosophical question. All these debates about how we should interpret quantum theory are maybe just not physically relevant. And one point that I would like to make very strongly is that the interpretations are actually physically relevant. And the only reason why the experiments didn't distinguish between them is because we haven't yet done the experiments that in the regime where the different interpretations and the predictions of the different interpretations are relevant. So the point I would like to also make in this introduction, and I will make that a bit more concrete in a minute, is that there are in principle experiments that will distinguish between the different views on quantum theory. Maybe they will not distinguish all of them. Maybe it's not possible to distinguish experimentally between Bohmian mechanics and many worlds and so on. But certain interpretations can be told apart from each other by actual experimental tests. And this I would like to underline with a few thoughts that I will present. And I'm actually not sure how many of you are already familiar with the different interpretations that exist. But if you want to know what does it actually mean to be an interpretation, then usually it's actually more in a sense than an interpretation. And that's why I would like to also immediately change the terminology and rather call them completions of quantum theory. Because what the interpretations actually do is they fill in certain pieces which are missing in the usual description. If you read a textbook about quantum mechanics, then the textbook tells you about the formalism. It tells you there is a Hilbert space, and if you there's a scalar product that is defined in that and that way. But let's suppose an alien would come to that has never heard about quantum mechanics, would read this textbook. Could he actually use quantum mechanics? The answer is no. The only ingredient he has a theory, and then he sees maybe actual things in reality, like maybe a glass of wine or something. And now the question is, how do I now apply this formalism to that? And the only way we learn about it is by looking at examples. But these examples are usually very restricted. The examples usually, at least in my class, of quantum mechanics consist of the harmonic oscillator and the hydrogen atom, maybe a few more. But we don't have a general rule that tells us this is the way we have to apply quantum theory or the formalism of quantum theory to reality. And that's the missing part. And what many of the interpretations do is to fill in this gap and say, this is actually how we do it in situations where we haven't yet tested it yet. So to make this a bit more concrete, let me briefly go back to this slide with the different interpretations. So for example, the Copenhagen interpretation, which is the one that is probably most, or has been most popular, would say that actually if you want to apply quantum theory, you first have to identify a quantum system and define kind of a boundary, which is usually called the Heisenberg cut, where you say this is the boundary where the quantum description ends, and around that is the classical world. And that's something that would, for example, be seen very differently in many worlds. or in Brownian mechanics, because there, if you ask what would people say about that, they would say, no, that's not true. You don't have to identify the quantum system at this boundary. The whole universe has a quantum state. There's a kind of a description of the universe as a whole as a quantum system. And that's what the formalism of quantum theory talks about. So you see, it's the same formalism, but one interpretation tells you apply the formalism to the whole universe as an entire thing, and the other tells you, no, you first have to identify this subsystem, for example, the hydrogen atom, and only apply the formalism there. So these are the type of differences between the interpretations, and I will go a little bit more into them. But I think what I said so far as Nicolas' face still looks very relaxed, is not anything that I would say 90% of professional physicists would not disagree with what I said so far. Okay, maybe we should test that. So who disagrees already at this point? Okay. Disagrees. Oh. So I was even too pessimistic. I thought 90%, because you always find people who disagree with you with the most obvious things, but maybe there are only reasonable people in this room. It's already a good start of the debate. But I will, of course, also now move into statements where we, I would say, hopefully don't agree, because otherwise it wouldn't be so much fun. So I will, at the end, say something about interpretations that Nicolas will maybe not like so much. We will see that. So maybe I should add, and maybe that's wrong, but you see here this ETH approach. That's actually the approach of the person you saw in the middle before, of Jörg Fröhlich. He developed his own approach, which he called ETH approach. So this is not connected to me, but of course I'm involved in discussions. Then there's the objective collapse model, and I think this is it wrong to say, Nicolas, you are one of the proponents of that approach? And so I will also say a few things about this. And I think we have already heard your opinion about many worlds. That's also not something I will defend. So what are now these experiments that we should do in the future to distinguish the different interpretations? And I think the key element that you need necessarily to distinguish the different things, and I think Anna anticipated that because she was already asking for intuitions about agents, we have to bring the agent into the picture. And this is the part where some people already would start to agree. There are people who say, no, of course, nature or the world already existed without humans, so we don't need an agent when we do physics. But let me here give actually a definition of what an agent is. I mean, a definition, it's not a mathematical definition, but it's what's the role of an agent? And this is indeed something where if you read different books or different papers about interpretations, it's not something people agree on. But my use of the word, which I will use for the rest of whatever I'm going to say in the debate today, is an agent, is basically a user of quantum theory. So it's the one person, if you like, or it could also be in that sense a machine if it's programmed with the rules of quantum theory, that is able to take in data about the world. So it has an interface to the world, maybe it can observe things, and then processes things according to the rules that it has learned about quantum theory that are programmed into that agent. And then it makes predictions and can again then maybe verify these predictions. So in that sense, an agent for me is just a user of the theory, but importantly, that user is also a part of the world. So it's not an abstract user that is just kind of hypothetically there. It's itself a system in the world. So in that sense, an agent has two aspects. It's basically a device that can reason according to the rules of quantum theory, and that's, for example, us, what we do when we learn physics. We are an agent in that sense. And on the other hand, it's a part of the physical world, and that's also us. So I'm not saying this distinguishes now, or this captures all features that you would typically assign to agents, but at least you should hopefully agree that if we say we are agents, we fit this definition. We are users of quantum theory and we are part of the world. But there are, of course, other things that may also fit the definition, but that doesn't hurt. Now, as I said, the Copenhagen definition would now actually talk about the agents in the sense that it would say we have to make a cut this Heisenberg cut that I mentioned before, which distinguishes the quantum system that the agent wants to analyze from the rest. And the only rule that the Copenhagen interpretation tells us, in addition to just the formalism, this is now already an interpretation-specific rule, is that this cut has to be outside of the agent, so the agent is not part of the quantum world, but of course it should at least encompass the system we are interested to study. So in that sense, there is this cut. And what I said before about many worlds is can be captured by this system, and many worlds person would say, no, we have this, we don't need a cut basically, or the cut is around the whole world. So these are the type of interpretation of differences between the interpretations, and obviously because these interpretations talk about the agents, we need to introduce the agents if we want to do experiments that distinguish the different interpretations. Now, as I said, I see agents basically as devices that can apply quantum theory. And what does it mean to use quantum theory? It means to reason according to the rules of quantum theory. And that's at the end an information processing task in a way. So you can think that this is, let's say, the physical system here on the left, but equally important are the agents who somehow can interact with the physical system. But what the agent also can do, they can think, they can reason. This could also be a computer who applies the rules of quantum theory, but at the end, the computer can, for example, say something about the system, what is its state, and then the computer or the agent, whatever it is, could make a prediction. So that's something we do when we make calculations in quantum theory. But I stress again, this could also be done even to a machine. So in principle, I could replace the agent by a computer that is programmed with the rules. And so in this particular case, this could be an experiment where someone prepares a system, one agent interacts with the system, prepares it, another one measures it, and I will later, as one should also give intuition about measurements, I will do that, but for the moment I just use the fact that we know in a lab what the measurement is. So one agent could tell what is the prediction, what would he predict about the outcome, and communicate that to another agent, and that would verify that. So agent can maybe communicate among themselves and process information. But this is again something that could be done by an automated device. It doesn't need a conscious observer. So this is important. I will not rely on vague concepts like consciousness, because if you go along this path, then the debate will probably not be fruitful, because I haven't seen any really reasonable definition of consciousness that is useful in the context of quantum theory so far. However, I would like to now introduce a postulate that I call the quantum information postulate, because it's very natural for a quantum information theorist to make that postulate. And the postulate is basically to say that once we have introduced agents, and I think no one can now deny that these type of agents that I've introduced actually exist, at least. Maybe they are not necessary for physics, but clearly they exist. We are such agents. Then if we want the physical theory to be a universal theory, the theory should also describe these agents, because the agents are themselves part of the world. And the universal theory of physics should be able to describe everything that is part of the world. I don't here say how exactly it has to describe them, but it should be general enough to describe them. And this brings me now to the problems we have with measurements. So, and here is the point where I have to talk about what measurements are. And I will actually take two different perspectives on what measurements are. So what I will briefly describe is the famous Wigner's friend thought experiment. And that experiment was invented a long time ago and gave us already hints that our current understanding of quantum theory needs to be completed. Or what people would have said, we need an interpretation, but I would rather say we need a completion. We need to say what's actually going on, and this doesn't follow from the pure formalism. So what's the Wigner's friend experiment? It's basically a very simple thing. We have an agent who measures a quantum system, and now by measurement you should really understand just the action, the instruction. So I could, in principle, or at least an experimentalist could give instructions to some other experimentalist what he would have to do to, for example, measure the spin. And what I mean by the measurement is just the sequence of these instructions that the agent would do. And at the end, because the agent is programmed with the rules of quantum theory, he can also interpret these results. So the Wigner's friend experiment consists of an agent here on the right, I call it A for Alice, who measures a system S, and then knows the result. For example, in this case, a spin measurement, the outcome could be +1/2 or -1/2. The only special thing about the Wigner's friend experiment is that this friend here, Alice, and the whole like equipment he has, the measurement device and everything, is assumed to be in a perfectly isolated box. So that's the only addition to what we would normally do. Now, as I said, this friend can now reason about things. For example, if he measured this, he would know now the state of the system is up. And if he measured -1/2, he would know now the state is down. But now the point of the Wigner's friend experiment is that there could be another agent. And this agent could be outside of this isolated box. And we could ask ourselves, how would this outside agent describe the entire experiment? Now, here is already a point where different interpretations would make different statements. And I think, let me here just go along one possibility. One possibility, but this is not necessarily true, is to say that, or is not necessarily what everyone would agree, here's really where the difference starts, is to say that because I just said this whole system is perfectly isolated, and because the formalism of quantum theory also tells you by postulate that the evolution of the quantum state of an isolated system is unitary, we know that the total state here in this system evolves unitarily. And now, once we know that, we can actually just ask ourselves, what's the unitary description of this measurement process as viewed from the outside? And clearly, this process should be compatible with what we know about measurements. For example, it should have the property that whenever the spin was up, the friend, so this is now the state of the friend. You see, the blue part describes now the blue part in this box, and the violet part here is the spin. So from the Wigner's point of view, so Wigner is the outside agent, the total state of what happens in this box is now that either the state is up and the friend, Alice, knows the state is up, or it's down, but because the evolution is unitary, it has to be a superposition of the two. I mean, what sign is here, this is just a matter of convention, but the point is, if it's unitary, there is a well-defined sign. If it was non-unitary, there would just be a random phase here and it would be a mixed state. But the assumption that it's unitary tells us it's actually in this state. And now the question is, do we already now have a contradiction? And here again, the different interpretations would disagree, because some interpretations, like many worlds, would say there's only one state of the universe. And if two people disagree on what the state of the universe is, which is the case here, because Alice would say the state of the spin is up, and this is not compatible with Wigner saying, no, the state is actually this so-called entangled state, the many worlds, or the many worlds person would already be unhappy and say, no, this was not correct. A shouldn't have made this conclusion. So we have a contradiction. Others, for example, I didn't so far talk about the Bayesian approach, cubism, they would say quantum states are something personal. So it doesn't matter that this guy and this guy have different views on what the quantum state is. And the collapsed person, like Nicolas Gisin, would just say, look, this system is just too big, there's an agent inside, therefore the state would have collapsed, and it's not true that this state is correct. But see, all these people would still use the same formalism of quantum theory, they would just add additional ingredients when we move to experiments that are beyond those we could already carry out, like this one. Okay, now I'm almost at the end. The point is now that I would like to make that here, in this experiment, we could still dispute forever what is now the right thing, whether or not this is a contradiction. However, there are newer experiments, and there have been several proposals, also by, for example, the group of Czeslaw Bruckner in Vienna, but also in Zurich we made a proposal. I worked on this with Daniela Frauchiger some years ago, and we proposed an extension of the Wigner's friend experiment. And in this extension, the idea is really almost the same as for the Wigner's friend experiment, except that the statements that the agents can make at the end are not about quantum states, but they're really about observable outcomes. So before we just the difference was just in what the two agents thought about the state, and they couldn't even communicate because one was in the isolated box. Here in this experiment we propose, which I will not explain in detail, I just say it involves rather than 4 different agents. You see there's one here in the box, there's one outside the box, there's another one in the box who thinks about the one in this box, and there's another one outside of the box. So at the end, the point is in this experiment you just apply the formalism of quantum theory and make again this assumption that in an isolated system everything is unitary, and you assume, there's an important additional assumption that if someone tells you something and you know this person is actually trustworthy in the sense that this person reasons according to the very same rules that you would use, then you can use that knowledge. So it basically means it makes sense that we talk with each other. Then under this assumption one can show that one of the agents arrives at the conclusion that a measurement outcome, not a quantum state, the measurement outcome is 0 and it's 1, which is obviously a contradiction. So we know, therefore, that if you apply the formalism of quantum theory using this unitarity, we are in trouble. And this leads to the following implication. And that's almost the last slide. And this slide should still make Nicola very happy. So I still need one that makes you a bit more unhappy. So you see, the objective collapse model survived this. So the point is, if you ask which interpretations of quantum mechanics can consistently explain such an experiment without giving up something which is really outrageous. Like you could give up this assumption that I mentioned before that we can actually talk with each other and make sense of what someone else says. Then this basically kills all these interpretations. For example, the quantum Bayesian approach would say the different agents, I mean, if you ask them what goes wrong in this experiment, people call this now the FR experiment. What goes wrong in this experiment? Then the quantum Bayesians would say, of course, the agent should never talk and exchange their knowledge. Each agent has his own view on the world, and they should not take any information from other agents and use them as their own information. But that, of course, doesn't make sense, because then we would have to redo all experiments in quantum physics that were ever done, because we could never believe a textbook, for example. So all these interpretations are basically not compatible with this thought experiment unless you give up something that you really, in my opinion, would not want to give up. But that's now a very opinionated statement, of course. And Nicola should already be quite worried that you are not the only one who survived this. You are actually together with Jörg Fröhlich. And so that would mean that in the debate I would have 2 opponents in Lugano, which I don't want. So I need to do something else, but unfortunately you're still in the same boat. So there's an additional argument one can make, which also rules out the beloved interpretation of Nicolas Gisin and the ETH approach, and this argument is the following. As I said before, the agents are just information processing devices. So we can, if you believe that we can build quantum computers, we can actually build such perfectly isolated boxes, because if you think about what happens in this box, this is an agent, but I've made the point very strongly that an agent could be replaced by a computer that just then processes information. Now a computer, of course, is maybe still very hard to isolate, but if you ask yourself, what do people who build quantum computers actually do? Then you come to the conclusion that what they do, and what's actually the hard part in what they're doing, is they have to perfectly isolate the information processing degrees of freedom from the rest. So they actually build de facto such a perfectly isolated box, where in the box it's not really a human agent, but it's an artificial agent, a computer who can still count as a user of quantum theory. So now, as soon as you do that, you have to basically buy the assumption that in an isolated box, things really evolve unitarily. Unless you would claim that quantum computers cannot be built fundamentally. And so that's the choice. That's why these crosses here are not white crosses. So this means maybe they can still be traded against something else. Namely, you could say, okay, you want this objective collapse model to survive, but the price you have to pay is to say quantum computers cannot be built. At least not quantum computers that are powerful enough to be programmed with the rules of quantum theory. And that's how I would lie the starting point of my opinion on the debate, and I'm really looking forward to see what Nicolas has to say about that. But the maybe message to everyone is, and there are mostly young people here, I think quantum mechanics is in a very interesting time, because I hope I convinced you, and this was the part where we probably all agreed still, that we need a completion of quantum theory. We are not yet done, because we don't know how quantum theory behaves in these scenarios that includes agents that are themselves in isolated systems. And we will probably be able to do experiments, for example, using quantum computers to test this. So we see a very exciting area of physics in front of us, where these so far just interpretational, or sometimes people say purely philosophical questions, actually become relevant and will be decisive to understand what is the right way to apply quantum theory to bigger systems. So I would like to end with that part, and now, or I'm not sure whether there should first be questions or of clarification. I think there was an idea that if there's purely clarification question, they can be asked now. I think that was the idea. Anyway, thanks for your attention so far. Yeah, so there is one question.
It's exactly on this last part, where you said that if one assumes that the isolated box is perfectly unitary, wouldn't, like, for instance, an objective collapse theory imply that there's a very small chance that there's a spontaneous collapse within the box, therefore removing this assumption that it has to be unitary within the box?
Yes, so indeed, that's a good question. The collapse theory would indeed say that in this box, each part has a certain probability that it will collapse. And of course, if the box will clearly consist very complex parts, like a quantum computer, for example. And so each of its parts has a small probability to collapse, but in total, the probability that it collapses will be quite large. And then one could say, okay, the collapse theory therefore tells us actually this thing will decohere, and therefore we are okay, that this contradiction doesn't arise. Now, the problem is those people who claim that they can build universal quantum computers, and these are the people I believe in, also have a technique which is called error correction or fault tolerance. So we actually know that despite the fact, so even in a scenario where the little pieces are all subject to errors, and the error could actually be surprisingly large, so it could be of the order of a promille or something like that per operation of a gate or something. So, and we know, at least in theory so far, that we can correct these errors. So actually it's not true that if we have 1,000 parts, and each part has a probability to decohere with probability 1%, that the whole thing will certainly decohere. Quantum error correction or quantum fault tolerance tells us there are techniques to circumvent that. This is a bit, in a sense, counterintuitive, but it's good you asked this question, because that's actually an important ingredient of the argument, to say that we can, otherwise we would immediately say, okay, universal quantum computers can anyway not be built because we always have some errors. But we know this is not true. So this argument is already ruled out by the mere existence of fault-tolerant computing, which was, by the way, invented, I think, at the beginning also by Shor, who already realized that to run an algorithm like Shor's algorithm, we would need some fault tolerance. So even without interpretation, he said, of course, in practice, we always have this decoherence, and he could protect against that. So in that sense, it's not an implication of the collapse models that things in this box will necessarily decohere, the information carrying degrees of freedom, and those are the ones which are relevant. Then I think it's time for Nicolas.
Well, thank you, Renato, for making my life difficult. I have to say that with Renato we agree on a lot of things. So to make also the debate a bit lively, I'm going to defend, of course, these collapse models and tell you how I think we should argue in favor of these collapse models. Although, see, there is not one collapse model. It's an entire family, or you may say a zoology, and so on. And certainly, I fully agree with what Renato said, namely that the time is really exciting because experiments and these quantum computers are coming, and so they will be also just progress on the experimental side, and it's only this kind of progress that will help to distinguish between these different interpretations. Some have already been more or less excluded, but we'll see. And probably there's also the need for imagination now. So I started with this title, No Reason to Give Up Realism. Okay, Renato, who is a wise person, didn't attack that part. But in many discussions, when you talk about interpretation, especially people maybe around many worlds, they will argue against realism or say that I'm too naive with my sort of realism. So I want really to defend that. I think it's very important. You know, physics is an empirical science, and we need to be able to do experiments and so on. If not, it doesn't make sense. It's not going to teach us anything. We're not going to learn anything about how nature does it. On the other side, I have this kind of subtitle, namely that realism and determinism are two different concepts, and I should not confuse them, although they are very often confused in these debates. So I'm keeping realism but not determinism. So what is the basic ingredient of realism? It's something very simple. Measurements have outcomes. I guess most of you are probably theorists, because it's usually the theorists who get interested in that. But I promise that if you go to an experimentalist and start arguing, oh, you're doing experiments, you're doing measurements, but your measurements have no outcomes, you're not going to convince the guy, and you're not going to become friends with, or he may just look at you saying, it's okay, something is not wrong, it's not going right with you. Measurements have outcomes. This is something which I don't think we should debate. This is point number one. If you start debating about measurements having outcomes, I don't think you can really, or maybe you should then quit physics and do, I don't know what, but not an empirical science. So these are already said, and I will elaborate a bit on that one. There's no reason to believe in determinism. Of course, we all know about scientific determinism, and all that comes back actually from the historical accident, which is named astronomy. You know, there's the moon that is orbiting, and all that is super regular, and you can easily predict and retrodict eclipses and things like that. But it's not because astronomy is super regular, and if it would not be regular, by the way, we would, of course, we as a human species would have never evolved. So this regularity is part of the essence. But that doesn't mean that everything in physics is deterministic. The weather and things like that are clearly chaotic and not necessarily deterministic. So just to finish on this realism, so the world out there exists and functions independently of humans, and I guess Renato and myself would agree here, and we can act on the world, but the world could also exist without us. So these are maybe really the basic assumptions I'm starting from. Then I have added two more points, but which are not of the same kind. So I think first, an interesting interpretation is something that should lead to new physics. I'm a physicist, and we want at the end to be able to do experiments and to distinguish these alternatives. And again, Renato said it very clearly. So here also we agree again. Again, I could name now some people with whom we could not agree on that one, for instance, and they come with interpretations that are kilometer long of words without any consequence. This I don't find it interesting. So fortunately today we are not going to debate about these uninteresting interpretations. And maybe also something, there is the theory, and we are developing theoretical models, and fascinating models, and so on. But nevertheless, despite all these successes, these are just approximations, and we should not confuse the model with reality. And reality is way more interesting and intricate. Okay, so that's the beginning. And then let me continue by just saying that all physical theories require interpretations. So there's a pretty famous paper in physics today that claims that quantum mechanics doesn't need interpretations. It's total absurdity. I mean, that was made very clear by Renato before. Yeah. If you just get a description with Hilbert space, operators, self-adjoint, and so on, unitary evolutions, that doesn't tell you how to handle that formalism and apply it. And here I want to take just one slide to talk about another physical theory, which is classical mechanics. And the reason why I want to go back to classical mechanics is that we all here probably have the very strong intuition that at least classical we understand. Beard balls and these things, these at least we understand. I'm not so sure we understand it. And I think we should really start from classical mechanics and ask how is it actually? Classical mechanics tells you a lot of strange things. First, it tells you that you have point particles, zero dimension, that contain mass and electric charges. How can zero dimension contain anything? It's a contradiction. Well, yes, no, we are used to it, so that's okay. Classical mechanics also pretends that if I move something, anything massive, that changed.
Sorry for interrupting. Please change the slide sharing.
I'll bring it back. What did she say?
Just share the screen.
I should. What is the screen was not shared?
Yeah, the screen is shared.
It was
Is
not
it
that.
okay now? Yes?
Okay, so I'm not going to touch it again. But, in principle, according to classical Newtonian mechanics, and gravitation in particular, if I move this thing, it has an immediate effect through the entire universe. It changes the gravitational field immediately everywhere, instantaneously, without anything carrying the information. That is totally absurd. And this is classical mechanics. So classical mechanics is not that simple. It's not so obvious. There are plenty of things in classical mechanics that should be questioned. And that at the end, by the way, about gravitation led to general relativity after several centuries of inquiry. Also, we need interpretation because we want to understand. Understanding is the goal. It's not just to do fancy technologies or fancy theories. We want to be able to tell stories how nature does it. So let's consider something very simple. Classical chaotic, something that doesn't work. Ça a marché. Okay, so consider a classical chaotic dynamical system, the atmosphere, the climate, things like that. And then ask the question, is that a deterministic system or is it not deterministic? So you have learned at school, university, about deterministic chaos. But it's not because you have learned that this is correct. So let's inquire, how does it go? Actually, you have this initial condition. You have a number, then you have the dot, and then you have all these digits that go on forever. If it's a typical real number, it never ends. It continues, it goes out of the galaxy, and it continues and it continues. And it's hidden in these digits that actually this future of a chaotic dynamical system is coded. So now, do you believe in this infinite string of digits? It's a matter of belief. Do you believe or not? Which is your interpretation? It has to do with interpretation, but now of classical mechanics. So at the end, whether this classical chaotic dynamical system is deterministic or not depends on the significance, the physical significance you associate with mathematical real numbers. These mathematical real numbers that typically contain infinite information. And so my slogan is the following: real numbers are not really real. You may buy it or you don't buy it. It's a matter of interpretation. So all these interpretation questions that are, of course, fascinating when we talk about quantum mechanics also exist in classical mechanics. It's not something special to quantum. And one thing which I think you should really understand is that the standard real numbers, they are actually the hidden variables of classical mechanics. So all this debate about hidden variables, Renato didn't use the word hidden variables very cleverly, but when we talk about interpretation of quantum mechanics, we very, very often use the word hidden variables. So he said completion of quantum mechanics. So you complete it with what? With something additional. Okay, maybe additional variables. And why not? But this is not something specific to quantum. Again, this exists already in classical mechanics. And actually, we are all using hidden variables when we do standard physics. And my claim here is that actually the situation of quantum mechanics is not that different. So it's good to know that already when we do classical mechanics, something that we have really the feeling that we understand intuitively so well, we have already quite often implicitly interpretation questions behind the scene. Okay. So the last slide here just wants to come back to these points 1, 2, 3. So most important point, measurements have outcomes. That's really the essential. And when I say measurement have outcomes, that already implies some form of a collapse theory, because it means at some point when you do a measurement, something comes out, some new information comes out. So a measurement produces a new piece of information. Consequently, the Schrödinger equation is not the full story. So it's not all unitarity. And also classical, if you now do the same with classical and you agree with me that real numbers are not really real, so this infinite series of digits are not all physically real, then of course, when you do a measurement, classical mechanics or the classical theory tells you that if you do a measurement, you would also get new information, and consequently, Newton's equation is not the only thing. But then comes the question, when does that really happen, this collapse or this new information? How is it that these measurements produce outcomes? And here I think there are different possibilities. So I'm now going into only one of the boxes of Renato and elaborating on within this box. A first possibility would be that this happens just spontaneously, that continuously or contiguously, nature produces new information. It just pops up continuously. Now, the amounts of this spontaneous collapse could depend on the size of the system. You have quite explicit models on that. And for instance, one of these models is this GRW, Girardi-Rimini-Weber model, quantum state diffusion model. Okay, intuitionistic mathematics, if you have questions, I'm very happy to answer them later. So one of the interesting things is that, so the general idea is spontaneous creation of new information, or spontaneous collapse, if you like. And then if you make it precise, like here, then you have one huge advantage. At least you could be wrong. And this makes your statement a scientific statement. As long as you cannot even be wrong, as many, for instance, many of the many world guys, they cannot even be wrong because they never make a prediction. So it's not really physics. So here we agree completely with Renato. We should develop alternative or completion, which at least can be wrong. So we can make an experiment and falsify it. So here, once you make it precise enough, you can be wrong. But of course, there are many ways of making it precise. A second possibility for when potentialities turn actual is that this is going to happen only when some very special conditions happen. And an example is, according to just unitary quantum mechanics, if I move again a mass, I'm going to have the gravitational field in if I don't move it, if I put my mass in a superposition of two possibilities, then the gravitational field will itself also be in a superposition of two possibilities. But at the same time, you know, that the gravitational field, according to general relativity, is the scene on which quantum things evolve. But now the scene itself would be in a superposition, and that gets very complicated. That's all quantum gravity and blah, blah, blah. And so people like these two people, Joshi, who is not very well known, and Penrose, who is very well known, but Penrose did it a bit later after Joshi, so let's call it the Joshi-Penrose model. They see that once we have this gravitational field in some relatively precise but large superposition this is one of the specific situations in which nature makes up its mind automatically. It has to according to this model. And again, this model has the advantage that it could be wrong. And people are trying now to develop experiments to try to test that. The same here. I mean, a lot of the parameters here have been already excluded about the GRW model. So these are two examples where at least things could be wrong, which is interesting. And the third and last possibilities that I see when to answer the question, when do potentialities become actual, is when a higher order level requires it. And this, the typical example is Copenhagen. Copenhagen interpretation tells you, you need a classical measurement apparatus. They don't really define it very precisely. So this third line of framework here, I don't know how to make it really precise, but it's certainly a logical possibility, and I believe it's one that deserves to be revisited. Of course, Copenhagen is old, but I think we should go back, maybe not to Copenhagen straight, but to this kind of top-down position. Possibly there is something to be found there. And just as a last point here, notice that only 1 and 2, these two frameworks, are compatible with reductionism. As physicists, we have been trained to believe in reductionism. Why should we believe in reductionism? Because we have been trained in that. That's not a good argument. But the fact is that if we really insist in reductionism, which I have to admit it has been a super successful principle to follow, a guide. So as a successful guide, maybe we should follow it, but then we need to work on 1 and 2. This one goes beyond reductionism and is too vague, in my opinion, today. So you see, I'm clearly on the collapse side because measurements have outcomes. No doubt that measurements have outcomes. Now, what about the quantum computer, since Renato left me with this challenge? Indeed, a complete quantum computer large enough to really mimic whatever we mean by an agent would be difficult or would be hard to make sense in this kind of framework. And maybe indeed we can make a large quantum computer, but maybe not large enough to be a valid agent. And maybe indeed the most interesting outcome of all quantum technologies is not to build a quantum computer that will break cryptography, but maybe it will be a quantum computer that shows, quantum technology will show the limitation of quantum physics. That would be maybe even a more interesting outcome than building a huge quantum computer. But of course, I don't know the answer. You may ask, what if a real quantum computer large enough to be to deserve to be named an agent exists someday, and indeed is in a superposition of having different opinions about having seen different outcomes of some measurements? I don't know. And I think this is maybe the best answer at the end. I don't think anyone in this audience, and Jörg Fröhlich is not here, so I'm able to really assert that. I don't think anyone knows. So I don't think I'm the only ignorant person in that field. Thank you.
So let's go to the discussion. So thank you very much for your introductions. Professor Renner, do you already have a reaction to Professor Gisin's introduction?
Yes, my main reaction is that I'm very disappointed that there are so few points where we disagree. Oh, okay, maybe more seriously, I think my main reaction is that there's one aspect that I think got neglected in your presentation, which is the aspect of what I would call relativity, because I would probably agree with most of your statements. Like I wrote up some, like I said, measurements have outcomes. And if you would always add relative to an agent, then I would be happy with all the statements you made. And I think this is kind of the point that, of course, it sounds very natural to say measurement have outcomes. It's as maybe natural as saying there exists time. But for time, we of course know, or there exists simultaneity. But in that case, we know, due to relativity theory, that this is a concept that is very strongly linked to the agent who says it. Of course, there is time, but the statement we make about time, and in particular what is, for example, simultaneity, is of course always relative to the agent. So we have to get used to say always that statement holds relative to an agent. And I think we should, in quantum mechanics, at least consider that option, that things that sound very natural maybe only sound natural because we are most of the time, like before we learned relativity, we thought, okay, we all see the same. We mostly see the same time, the same simultaneity. We usually see the same outcomes. If something happens in this room and there's an outcome, some light flash, we will both see it. But in more intricate settings, or like in relativity, when we go to large velocities, but when in quantum mechanics, when we go to experiments where we really have control on all degrees of freedom, then we should probably, I would advocate, always say relative to an agent. Maybe I'm advocating that even too much, because I realized at some point in my group when I said, let's suppose we have two agents and there is an event happening. Then some of my PhD students were really looking at me very surprised. Said, do you seriously think there's an event happening? Because I didn't say relative to both the two agents. It's something extremely important, I think, to add that. And if once we add that, then I think we can even converge to the same view. Because then even things like when you say, okay, of course there is a collapse if I see a measurement outcome, I'm happy to say that there is a collapse relative to the agent. And what it means is basically what the Born rule tells us, that there is a certain probability that we see outcomes, but not more. Not that physically there happens something now fundamentally different just because this person measured.
Okay, so I'm not sure I understand. If we go back to this, the figure you had with the Alice in the box and Wigner outside. So let's suppose there is a measurement outcome relative to Alice inside the box. So is it now still correct for Wigner to describe this box as a superposition of all possible outcomes, or is there one outcome, let's say the outcome relative to Alice, that is really secured?
Yes, I would say it's only the outcome relative to Alice, in the same way as if, let's say, to then make the picture in relativity theory, let's say, let's suppose, for example, there is only one particle in the universe. This particle has no velocity because there's nothing it can have a relative velocity with. So we would say the information whether it has velocity doesn't even exist. And now, if there was one agent there, suddenly then this agent could now say this particle has a velocity relative to it. But let's suppose there is another agent who would never have access to that universe, let's say he's in a kind of disconnected one, then he could not talk about the velocity of that particle. So in the same sense, I would now say in this particular situation, because there's this perfect isolation, which is making things, bringing it away from our daily life intuition, because as soon as, of course, Wigner opens the box, we we disagree again that they both see the same. But I would say, no, we maybe have to get used to the idea that this event only exists now relative to Alice in the same way that a velocity, for example, only exists if I have someone relative to which I can define this velocity. And it wouldn't change anything in Alice's perception. So everything we know that, of course, if I do a measurement, I see the outcome would remain the same. But it would change things if we do these much more elaborate experiments that we cannot do now. So I think they will decide on that. And I think we should, I'm not necessarily saying this is the true thing that will happen, but I'm strongly advocating for not neglecting that option at all and say this is a reasonable option. We were often enough in physics misled by thinking things are absolute. And I shouldn't make this mistake again.
Okay, we disagree on that. What can I say?
So you disagree that things could be relative?
No, I think
Oh.
measurement have outcomes and we have absolute outcomes. I don't think your analogy with time is that relevant. I mean, time indeed is relative. I mean, we have learned about that. But measurement outcomes for an agent like Alice, let's think of a human or a super sophisticated computer, they have a real outcome. At the end, either the flash, the lamp flashed red or flashed green. And that is an objective fact.
I should say it's actually a very positive thing that one can localize the disagreement, because in most discussions one has with physicists with different interpretations, they usually go in circles. One always says something and then they say something else and so on, and at the end one doesn't know where we disagree. I think now we already localized our disagreement. I think this is really probably the point, that one can say it here, one can have different opinions. Should an event be absolute or not? Yeah. But I wouldn't even say this is excluded. I would say this, to our the best of our current knowledge, it's a possibility that it's relative, and it's also a possibility that it's absolute. But I'm not ready to just go along one route and exclude the other.
I think there was a question.
No. How do you define an absolute outcome in the case if Alice is a quantum computer?
I mean, the quantum computer will have only one, will no longer be in a superposition of having seen red and green. The computer will be in a state having seen green, or possibly in the alternative state having seen red.
It will not be
a quantum computer does not need to be always in a superposition, a maximal state of confusion. It can also have one outcome. I mean, usually quantum computers are expected at the end to give you an outcome. And the outcome will be factoring a certain number, or will be the shape of some molecules that are specifically, especially efficient for some tasks.
But then when you are obtaining the results from the quantum computer, you are adding a third agent that is reading the result from the quantum computer. So in the perspective of the quantum computer,
So
can he be in a superposition?
You know, there's indeed one interesting alternative, which maybe you find interesting. It's solipsism. You can indeed start with this kind of discussion that, you know, there is this Alice, and as long as you don't talk to her, I mean, she doesn't, you don't really exist, and so on. Solipsism is a logical possibility, and a highly uninteresting one, in my opinion. So being logically consistent is not sufficient to make it interesting. And so for me, this agent, Alice in this chaos, Renato named her, indeed sees an outcome, and this outcome is the result of her measurement. And I'm not going now to try to elaborate and say what happens if something else comes, and then maybe it erases her memory and changes her opinion backwards in time because she thought she saw something, but actually she didn't see it. No. Measurements have outcomes.
Can I ask maybe a question to clarify that point, because that's maybe important. But okay, maybe I should first say I firmly believe you exist. But now, given that you exist, what you said is so would mean, if I understood this correctly, that we can actually do an experiment to distinguish our two opinions. Namely, I would now say, no, the quantum computer that is in this experiment that simulates Alice in the box would actually still be in a superposition, and now we could come with a measurement device from outside and check whether it's in this superposition. And if I understood you correctly, you would now say the outcome of that experimental check would tell us no, it was actually no longer in that superposition. Yeah. Is that the correct understanding? So it's really you were saying it's a physically very
partially because then what is a large enough quantum computer? And here you have to come back to my points number 1, 2, 3 to tell when potentialities turn actual, or maybe in this different language, when superposition turn into an actual outcome. And so you need to really build an entire model which has to make predictions so that it can be wrong. And so you may say maybe this happens only if you have these very specific situations like the superposition of the gravitational wave field. So if you make such a model, possibly you can falsify that. That is possible. Or also if you say it happens continuously a bit a la GRW, these spontaneous collapse models, then again, you can indeed make an experiment, and people are doing these experiments and are possibly ruling out some models. But to rule out all possible models at once, as we can do with Bell inequality in a different context, it's not interpretation, but locality, not locality. This, I don't see today how to do that. Because, if you take really a baby quantum computer, those that already exist today, of course, you can put them in a superposition of 2 states, but I wouldn't call these baby quantum computers an agent. And now, how large does it have to be really deserve to be deified to the status of an agent? I don't know. For that, I need to develop a model which is explicit enough that it makes predictions and possibly could be wrong. And we should certainly do that, develop these models.
I think I agree with that. Okay, really, I'm getting a bit worried that there are really too many things we agree on. It's going to get boring, but I agree that I had this model of an agent that it has to be complex enough to be able to use quantum theory as an information processing device. But I see the point.
Precise enough to be wrong?
No, yeah, I mean that definition I think is precise enough because I can say if it's complex enough so that I can program all the rules of quantum theory that I consider relevant, which of course have to be proposed. But I agree that you can now come and say this is still not an agent because a real agent also has a gravitational component, which maybe a quantum computer is designed in such a way that the overall gravitational field from the outside doesn't move. And then indeed I would say, okay, then we also have to build that. So I think the point you're making that there's no universal test of everything is a good point, and this also makes it difficult to actually maybe convince everyone at the end. But I think that's also a reason why it is actually an exciting time because, for example, I'm a very big proponent of these quantum gravity experiments or low energy quantum gravity experiments where we test whether a gravitational field can be in superposition. That's extremely relevant to exactly rule out such things. And these are just experiments we need to do. I think we can debate forever, but here we have to ask nature what it does, and then we know the answer. And I think we should do that. But maybe just related to gravity and relativity and so on, I think here's a point to make that people who work in quantum gravity, they often actually are not so much aware of these foundational problems in quantum theory. So often they implicitly assume that there is actually a sensible concept of saying the whole universe is in a quantum state. And then they argue about how this is now incompatible with gravity. But my point would be that if you make such assumptions, maybe you're already, before you bring in gravity to the picture, you're already inconsistent in quantum mechanics itself. So I think my advice to people working on gravity is to be very careful with statements like there is a state of the universe and so on, and ask themselves whether there are already contradictions at this point before you bring in gravity, because this is most likely actually the case. I think it's very important to actually convince more people to think about experiments at the interface between gravity and quantum mechanics, because this is data we need to make progress in the debate.
And we can again go back to classical mechanics. So I try to very briefly argue that classical mechanics can be considered deterministic or not, depending how you view real numbers. And here you can just say, oh, I buy the real numbers, these are my hidden variables, and I make chaotic dynamical systems deterministic, or you reject this infinite information of real numbers, and then you say it is non-deterministic. But as long as you stay within classical mechanics, you cannot answer. It's just a matter of an opinion or a belief, and so on. So how did we actually make progress? Clearly, we made progress because we discovered quantum mechanics and quantum theory. And quantum theory then tells you that indeed it is the indeterministic side that is the correct one. But if you stay within classical mechanics, you could not really make this progress. And so I'm not completely sure that staying just within this frozen framework of quantum mechanics, we will be able to answer these deep questions. Maybe we need indeed to bring in gravity, or maybe we need to bring it top-down causation, or maybe we need, I don't know what, but we need for sure something that comes from experiments. We need some data. It will not be sufficient to just be talking about it. I mean, it's fascinating and so on, but the main conclusion at the end should be, let's go and do some experiments, and before that, let's develop theories. And when you develop theories, never be afraid of being wrong, because one thing that is way worse than being wrong is to come up with a model that cannot even be wrong.
Can I ask you a question about that? So I had this picture with some interpretations, and one of them was the collapse interpretation. How likely do you think that once all these experiments are done and we know more, is the answer within that chart, or how likely is it that it's actually somewhere completely different and we have an answer that we couldn't imagine now? In a similar spirit as if we go back in physics and ask ourselves, how did people actually, the guesses they had before relativity theory was invented, before quantum mechanics was invented, I think they were very far off. Yeah. So how likely is it for you that indeed you will say, it was just this collapse theory? I find this very unlikely, to be honest.
Well, I think at the end it will be one of these collapse models, but the argument for it will probably go a long, long way around it. And again, my intuition is, again, coming from classical mechanics. Indeed, at the end, we know that there are no hidden variables, so these classical real numbers that are the hidden variable of classical mechanics are excluded, but they are excluded going an enormous detour via Bell inequality, non-locality, and all that. So at the end, the answer is very simple. It's indeterminism. But the argument is goes way beyond classical mechanics. And probably the answer, which collapse model is correct, may also go way beyond quantum theory.
But the relative collapse model would not be what you would expect.
No.
So if you were to design those experiments to choose an interpretation, what are other parameters that would be relevant? You spoke about the age and the measurement. Are there other things that would be very important to look at?
Well, it would be good to be able to quantify complexity. It has to do with complexity also. You know, these quantum computers, for instance, they become more and more complex, and you have to handle all these error correction codes and all that. Could it be that at some point we hit a complexity wall? I don't even know exactly what I'm saying when I'm saying that. But I have the feeling we don't understand complexity well enough.
I think maybe as physicists, and as in particular as quantum information theorists, we, myself included, got a bit spoiled in the sense that we had an abstraction, like we started from physics, and then some people had this idea we could actually abstract from physics and just talk about qubits, which are very, think about it, extremely abstract mathematical thing, maybe as abstract as real numbers. It was the same in classical mechanics, and these abstractions worked extremely well. And I think this was a problem exactly because they worked so extremely well, for example, in classical mechanics, people, in particular maybe mathematically minded people, suddenly thought these real numbers are real. And I mean, here I again agree with you. There's no reason to do that. This was just a model. We had experiments which always had a very finite precision, and then we made a mathematical model, and the mathematical model abstracts in unimportant part. But this doesn't mean that the abstraction that comes out of it is actually the real thing. It's an abstraction. And now in quantum information, we often do the same. We just think we can model the whole world in terms of qubits and stuff. And we forget physical aspects. And I think one aspect that is completely lost in this abstraction process is, for example, the notion of reference frames. So whenever we talk about a qubit, we of course have an actual physical system. Information is always physical. And this is, for example, a spin with a direction. And that direction only makes sense relative to someone who has a reference for direction. Now, it's my firm belief that we have to reintroduce that aspect on a very fundamental level again in order to capture everything. So I think the parameters that will determine an agent is also its functionality as a reference frame. Because whenever I do something, I always think of the empty universe with a particle in it. I can only measure the velocity of the particle because I'm myself part of the universe, and the velocity is defined relative to me. So I think this is an aspect that we don't have if you just talk about qubits, and also if you talk about complexity only. I think complexity is important, but I think this is the aspect, the parameter we need to add. A system has a weight, it has an angular momentum, it's acting as a reference frame. So this is important to bring into the experiments.
So the mathematical framework would be an obstacle to physical interpretation.
It's misleading. No, I think it's not an obstacle. I think abstraction is great. I'm a big fan of abstracting unimportant things away, but we shouldn't forget that we have done that and not make conclusions that leave the range of validity of the abstraction. And I think this happens. It's the same that really happened. I think the real numbers are an excellent example, because obviously no one of the experimentalists would ever have claimed he has done an experiment where he determined a real number. But then, of course, it's very cumbersome to always, in the mathematical theory, include a finite precision. So people said, let's just forget, let's just, to make our lives easier, forget about the finite precision and describe things in terms of real numbers. And then maybe a few hundred years passed and people suddenly thought, okay, these real numbers were always there, no one contradicted them, so they are actually real. And this is a big mistake. So which doesn't mean the abstraction was bad, but an abstraction has limitations, and we always, as physicists, you shouldn't think too mathematically. You have to understand that these questions are mathematics. I mean, usually the mathematics students in lectures always come with these questions. What does the delta potential mean, and so on? I think the answer is always it's an idealization because we made an abstraction, and then this makes sense. But if you had a more concrete physical description, this thing wouldn't even exist. There would be no point in writing a delta function or stuff like that. So I think we should just not take the abstractions too seriously. But this doesn't contradict the fact that they're extremely useful to understand things. For example, the Bell inequality is another example. It's a very abstract model, but it exactly captures the right ingredients we need to understand why there are no hidden variables. But it's just
local
for that.
hidden variables.
Yes, no local hidden variables.
There was another interesting point that you mentioned in your speech. It was the consciousness, and that it is not relevant for the interpretations. What do you think about it? The consciousness and free will?
Well, so I certainly believe in free will, but I don't think it is relevant to physics. More precisely, I don't think physics today has anything meaningful and interesting to say about consciousness and free will.
So it shouldn't be taken into account?
Well, we should certainly be cautious not to believe in a theory which excludes the possibility of free will. But we don't understand enough to be able to say anything meaningful about consciousness and free will. Mm-hmm. Not today, I don't know. Okay, in 100 years I have no idea, but today I think we have nothing interesting to say there.
Maybe a last point that we could address is the many worlds interpretation.
Yeah, in many words, you can kill yourself and you survive in another brand.
So yeah, any thoughts on this?
Well, it is a quite annoying thing because there are a lot of mathematically oriented theorists that love their formalism so much that they believe in the formalism more than in the physics at the end. So it is a bit annoying because when these people, they just tell you, oh yeah, of course it has, everything exists, everything, we're in a superposition of all possibilities, this debate happening, this debate not happening, and everything else happens in superposition. I find that, what is the explanatory power? Again, we want not only a theory, we don't want just unitary operators and beautiful Hilbert spaces. We want stories. We want to be able a story of how nature does it. And many world doesn't provide any explanatory power. Explanatory power of meaningful is exactly zero. It's completely vacuous. And so I'm good that you didn't invite a many world guy.
She did. So I actually went through that phase.
Yeah, but you were cured. I cured you.
Yeah, yes. I was surrounded by enough wise people. But I think you described it very well. I fell at that time in love with the formalism of quantum theory. When you learn quantum information, for example, you suddenly see there's so much you can do with that formalism. It has to be the right formalism to describe the world. And in that formalism, there is no collapse mechanism. So I thought the only possibility to make this, let's say, to relate this very beautiful formalism to the real world is many worlds. But then, I got cured as I got a bit more mature. And so the point is, I think I would also add one additional point, which for me speaks against many worlds, and by the way, against many other interpretations, not, by the way, collapse models. I think this is the big exception. Many of these interpretations have very vague elements in them. And I think this is the big advantage of collapse models. They usually make concrete what the collapse mechanism is, or they have to do that, as you also said. But in many worlds, there are notions like the branching process. And I've done a lot of, as I said, I was a big fan of the model, and I tried to figure out, but when does now this branching happen? And I never got an answer. That was part of the reason why at some point I lost interest in that. And I think it's just not well defined because, it's certainly true that there are now many worlds interpretation, and all these many worlders will give you a different answer of when does the branching happen. Some would even be not, have many opinions themselves as one many worlder. So you never get an answer to that. And I think this is one requirement I would impose to any interpretation. So as I said, I would no longer call them interpretations but completions. And then it's something physical, but if in order to be a physically relevant theory, you have to make a statement that is falsifiable. As Nicolas also said, you have to potentially be wrong. And if you just make the statement so vague that it cannot even be wrong, then you have not succeeded as a physicist. And in my opinion, many worlders do exactly that. They have a very vague notion of what this branching is. And of course, I cannot blame them. It's very hard to find one. But if they want to claim that this is a good theory or a completion of quantum theory, they need to go through the process and define what that is. And some do. I'm not excluding everyone, so I'm sure there are some who do that homework, but there's no common agreement on what that should be. And I haven't seen a consistent description that would, for example, then, if I apply to the Wigner's friend type experiments, succeed. And I even have an argument, which I'm not going to present. This could be another thing, which shows that whatever thing you would come up with, like branching rule, you will run into contradictions. And I think there are also people in this room who also worked on that and came to similar devastating conclusions about many worlds. So I think it's, in the first place, just ambiguous. And that's an even more severe criticism in the spirit of my older colleagues who already passed away, Pauli, who used to say that something is not even wrong. So I would say many worlds is not even wrong.
Okay, well, thank you very much. We can. Are there any questions in the audience? If no, we can take it to the apero. So yeah, thank you very much.